As we move on in our meteorology unit, today we're going to go ahead and start looking at frontal boundaries. And this is where air masses do battle. So here's what this first little graph is. So I'm going to start with this and I'll end with this. That there are the time and space scale of our atmospheric motion. And it kind of takes a minute to process that. The time and space. That how long does an event take place and what's the size of it? What's the magnitude of it? So the magnitude is the geographic size and the lifespan is the time. These are important for considering how a weather phenomena can act on a location. So if I talk, I'm going to start off with seconds to minutes on a very, very small scale. These are what we call turbulent eddies. That a turbulent eddy could be something, an example would be like a convection current. Very, very short-lived. Air could be rising, air could be descending. It's just a very short-lived energy. It's on a small scale, micro scale. And they last seconds to minutes. On a slightly larger scale, which is referred to as like a mesoscale, severe weather. We can call it thunderstorm, tornadoes, waterspouts, dust devils. These are relatively short-lived in semi-small scale. These can be, you can find them and pinpoint and say, hey, there's where that's happening. But a larger scale yet would be a land or a sea breeze, a mountain and valley breeze, a Chinook, Santa Ana winds. These are on just a slightly larger scale than severe weather here. These are moderate lifespans. They last a little bit longer, and they can be a little bit larger in scale than obviously the severe weather. Then we have hurricanes. Hurricanes are on the synoptic scale. Let's just say a much larger scale, right? Roughly 2,000 kilometers in size. Larger scale, longer lasting. They last greater than these hours and days. They last more like days to up to a week or more. And we can talk mid-latitude cyclones. These are very large scale and long-lived. These last about a week, and they cover pretty much the entire continent of the United States before they dissipate over the Atlantic Ocean. And then long waves. Long waves are where we have infrared heat energy that's re-radiating back into our atmosphere. And these are on a global scale, right? We look at insolation patterns, and these last weeks, months, etc. These are large scale. So long waves, right? The infrared, the heat energy re-emitted in space. But we're going to be focusing on this area right here, the weather features. So weather, we're going to be talking about fronts. So we're going to need to know the differences and characteristics between warm fronts and cold fronts. We're going to describe the cloud patterns associated with warm and cold fronts and identify characteristic slope of warm and cold fronts. What's very important here is that we recognize that a cold front, right, a cold front denoted by this blue with sharp edges on it, it's moving to the right. So the sharp edges are kind of pointing in the direction which it's heading. And we have cooler air or colder air that's moving into or aggressively faster than warmer temperatures. So we have cooler air pushing into warmer air. And on a warm front, we have these rounded features, generally in red. Warmer conditions are moving into cooler conditions. And so if I look at these pictures here this cold front is saying, well, I've got 28 degrees, 31 degrees. These are probably generally Fahrenheit, moving into an area that's 55 degrees Fahrenheit. So it's cooler air moving into warmer air. And here I have warmer temperatures moving into cooler temperatures. So those are what defines my boundaries that I call a warm and a cold front. So the symbols, here I have my warm front. Cold front. Here I have my warm front. I'm getting ahead of myself. Here I have a stationary front. And here I have an occluded front. Now, this is what it looks like when we talk about a trough. And we'll point those out. I'm not really going to test you on it, but I want to just make sure that the dotted lines, we find them on maps that we'll find on the Weather Channel pretty regularly. But these are generally these five. This four are the frontal boundaries. This is a little different, but we'll find this. We'll be able to identify that. So our frontal boundaries, these are boundaries that separate air masses of different densities. So an air mass, they retain their identities, that they don't change. They simply retain them. That cooler, denser air acts as a wedge, and warmer, less dense air is forced aloft. So make sure we pay attention when we look at maps. High and low pressure means something very, very specific. This is the centers of the barometric pressure. That low pressure, we're going to be looking to find storms and clouds and these potentially severe conditions. High pressure, we generally find fair skies, pretty relatively clear. So these are just another way of kind of depicting those frontal boundaries that we've looked at. So moving on, the four types of fronts that we will study. A warm front, where warm air is invading cold air. Warm air is what I'm going to call moving aggressively into cold air. And a cold front is where cold air invades warm air. That cold air is moving aggressively into warm air. A stationary front, it's essentially like neither air mass is moving towards one another. They're kind of somewhat stationary. They're kind of locked in place. And an occluded front. This is where cold air overtakes warm air and rides under it. So once again, we can go back to the original pictures we looked at. Cooler air moving into warmer air moving into cooler air, and warm air and cold air kind of locked in place. They're kind of along this boundary, we'll find the potential for precipitation. So let's look at a warm front. This warm front is where warm air replaces cooler air. That it's shown on a map by a line with semicircles, and that's what we see in red. I could even add red line with semicircles. It has a very gentle slope. And gentle is very important here. That when I look at this picture, this slope would be about whatever your measure, 1 mile in elevation for every 200 miles is your run. So your rise and run. Remember, that's what a slope is, rise over run. So very, very mild here. That clouds become lower as the front nears. In other words, if I'm standing right here, I'm going to be able to see this cloud sequence of cirrus clouds. Remember, the cloud's moving to the right as I stand right here. Cirrus clouds, this is my cloud sequence, denoted by the letter C. Then I would see cirrostratus clouds. Then I'd find altostratus clouds. And then lastly, I'd find nimbostratus clouds. And where I find nimbostratus clouds, I have the potential for light to moderate precipitation. But this is moving very, very slowly. So warm fronts move very slow. They have a very gentle slope. And warm air is overriding cool air. So the warm front itself has this particular cloud sequence. I'm going to go back and go over it. That your cirrus clouds are going to be your highest elevation clouds. And then your cirrostratus clouds, your altostratus, and your nimbostratus. And notice, the reason why we get this cloud sequence is because the gentle slope is going to have let's just say the moisture are going to form different clouds as it overrides the cooler air below. And finally, where you find nimbo is kind of a term that refers to the potential for rain. So warm air moving aggressively or faster than cold or cooler air mass is where we find our warm fronts. The boundary of the collision is the warm front. The warm air ascends, generating a predictable cloud sequence. Where a cold front is going to look tremendously different than the warm front. That cold air replaces warm air. Remember, it acts like a wedge, so it's pushing warm air up. It's shown on a map by a line, a blue line, with triangles, right? It's showing you the direction it's traveling. It's twice as steep as a warm front. So every 1 mile rise for every 100 miles run. Much, much steeper. The steep slope is going to be significant. It advances faster than a warm front. Cold fronts move much faster than warm fronts. And cold fronts here, associated weather is more violent than a warm front. The intensity of precipitation is greater, but the duration of precipitation is shorter. So a warm front can be longer-term, longer-lived precipitation, but no severe weather. Whereas a cold front can be very severe, right? Cumulonimbus clouds are associated with cold fronts. Very, very intense precipitation potential, just a shorter duration in which it's going to take place. So my cold front, this is the cold front. It's advancing cold air behind the cold front itself. It's moving into the warm air. It's pushing the air aloft, and you're creating these cumulonimbus clouds. That the weather behind the front is dominated by a colder air mass, so the temperatures are going to drop. The air is going to be sinking behind it, subsiding air, and the conditions are going to clear out. So a cold front moving through actually clears out the air behind it. So even though the temperatures are cooler, generally the conditions get much, much clearer. So the cold front is where the cold air moves aggressively faster than the warm air mass. That the boundary of the collision is what we call the cold front boundary itself. That where we find this cold front, we find cumulonimbus clouds. Severe weather potential comes with it. That this cumulonimbus cloud, this anvil shape, if you will, is where you can find heavy precipitation, you can find hail, you can find downdrafts of winds, you can find tornadic activity potential, you can find severe thunderstorms, and with that including lightning. So you have the potential for severe weather when you have cumulonimbus clouds at a cold front boundary. Not so much with the warm front. So let's look at this real quickly here. So we can have other clouds associated with it, but the quick change can get very, very severe with the cold front. As a cold front advances, cumulonimbus clouds develop and evolve. This is the key here, they evolve. That other clouds can also develop in the process in front of the cold front. We can look at this alto cumulus cloud, and these are these clouds that are kind of puffy. They're kind of mid-level clouds that you start to see that something's happening. They're evolving. But you can also have out in front of them, notice where you get this fallout, where air is rising. You can actually get the cirrostratus cloud and a cirrus cloud. These are high level. This is kind of the air fallout from this updraft of air that's rising. Remember, cold air wedging beneath warm, moist air is going to force it aloft. But notice the wind directions and the wind speed is going to change. And notice the temperature change before 50 degrees Fahrenheit and after 39 degrees. So your temperature is going to change. So we're going to be looking at these conditions of what's taking place within the cold front and the warm fronts themselves. So stationary and occluded fronts, two other fronts we'll look at. A stationary front, the flow of air on both sides of the front is almost parallel to the line of the front itself. That the surface position of the front does not move. That it's just what it's called, stationary. That an occluded front, this is where active cold front overtakes a warm front. And we'll look at this. I've got a picture of this on the next slide here. We'll be able to look at this. We'll talk about this sequence of what's taking place. That cold air wedges the warm air upwards, right? Cold air always is denser. It's always going to wedge the warm air upward. That the weather is often complex, and precipitation is associated with warm air being forced aloft. So let's look at this picture. I have cold air. I have this cold front. I have a warm front. Here I have my cumulonimbus cloud, and here I have my cloud sequence with my cold front. But when they collide, I can actually have this complex weather because I have air rising on either side. But this here can be short-term, can be long-term. It just depends on the rate of the air mass movement. But the occlusion takes place once your cold air then eventually rides underneath your warm front. And this is my occlusion right here, right? My occlusion begins when the cold air starts lifting or picking up the margin, the end of my warm front itself. And then your rains change, becomes more moderate. Notice it's cold air moving into cool air, still forcing it aloft. We're saying that cool is, let's just say, has more temperature, more heat than the cold. So I'm going to go back and finish with this slide here. Go back to the time and space scale of atmospheric motion. That the magnitude, right, the size of the amount of area we're looking at, and the time at which the weather pattern, the atmospheric condition exists are important for considering how the weather phenomena can act at a location. So once again, we can compare all of these. I want to go back and make sure you understand that some of them can last from seconds to minutes, from minutes to hours, from hours to days, even days to weeks or more. But some of them can be, for example, like our thunderstorms. These normally last from minutes to hours. That we're kind of this smaller scale weather phenomena. And some of them can last up to days. Obviously, we can have rain for a couple days. But in general, the severe weather is very, very short lasting. And it's on a scale of roughly, 20 kilometers, on a small scale, the mesoscale. A much, much smaller scale, that it's fairly localized. And we have these different features that can take place. Turbulent eddies, severe weather, land and sea breezes, hurricanes, tropical storms, mid-latitude cyclones, and long waves. It's the heat energy re-radiating into the atmosphere. That they have different sizes and different lifespans in which they take place in our atmosphere.